The maximum flow problem is about finding the maximum amount of material able to move from a source, which produces the material, through a finite network of routes to a sink, which collects the material. For example, if water is the material, we may have a water source such as a lake or spring up a mountain. The water will flow from this source into a sink, somewhere the water collects. This could be a puddle, a lake, or the ocean. The source in the mountain produces water which collects in the sink or the ocean. The water travels from one to the other through a finite set of routes, in this case a network of rivers and streams. This is a very literal example. We need to abstract it in order to calculate the maximum flow. The best representation of a network like this is a graph. So we add a single source node and a single sink node. The graph needs more nodes than just these, so we are going to add nodes at points where two or more water channels join. These are intermediate nodes, and they neither produce nor collect water. All water which flows into an intermediate node must flow out of it again, and vice versa. The rivers and streams in our example can be represented by directed edges. Of course, we need to add weights to these edges in order to represent the volume of water that each stream can hold, the maximum amount that can flow down that edge from one node to the next. The weight of an edge is referred to as the capacity of that edge, and you cannot have more water flowing down an edge than it is capable of holding. Note the yellow edge from node 7 to the sink node. I've highlighted this edge because the algorithm we are going to use requires that there is only a single source, a single sink, and no parallel edges. We can remove the parallel edge by adding another node. Note that the capacity to and from this node are the same as the original edge capacity. We are not looking at something the length of an edge would affect, but rather how much material can pass through the channel. Adding an extra node doesn't change the fact that only 7 units of water can travel down that stream, so the capacity of the two edges is still 7. Now we can remove the literal background and abstract the model. This type of weighted digraph with a source and a sink is known as a flow network. Here are some quick definitions we've already covered. Feel free to pause. The algorithm we are going to use is the Ford-Fulkerson algorithm. This algorithm works by selecting a path of edges which are not at capacity already, and increasing the flow down these edges until there's no path of edges from the source to the sink where every edge in the path is under its capacity. To make choosing paths easier, we introduce a new residual network. The residual network replaces every edge with a pair of edges, one in each direction. The edge in the residual network which matches the direction of the original edge represents the additional amount of material which can flow down the edge before it reaches capacity. The edge in the opposing direction represents the current flow down the original edge. Summing both the edges in the residual network gives the capacity of the edge in the flow network. This is a less messy version of the flow network we had before. This flow network is currently just showing capacity as there is no flow through the graph yet. To keep things simple, we hide edges with zero capacity. This means that the initial residual graph is actually identical to the flow network above. Using this initial residual network, we choose an arbitrary path from the source to the sink. This path is called an augmenting path. It is a simple path with no cycles and no more than one edge between each node. We're going to increase the flow down this path, but we're limited by the minimum capacity. The maximum quantity of water which can flow down the path is the smallest quantity which pushes an edge to capacity, the minimal capacity. This limiting minimal capacity is called the residual capacity. We augment the residual network with the residual capacity. You can think of this as a fancy way of saying we add the residual capacity to the flow down the edges in our path which match the edge direction in the flow network, and subtract the residual capacity to the flow down the edges in our path which oppose the flow network's edge direction. On the right, we can see the added flow on the flow network. The number before the slash is the current flow down the edge, and the number after the slash is the capacity of the edge. On the left, we see the modified residual network. Remember that current flow down an edge is represented in the residual network by an edge in the opposing direction to that of the flow network. The remaining capacity is shown in the same direction as the corresponding edge in the flow network, and in this case, 3 of the edges we chose have reached capacity. Since the remaining capacity for these edges is 0, there is no edge in the residual graph in the direction of the original edge in the flow network for these edges. We now choose another augmenting path on the residual network. The residual capacity of this path is 4, which is the minimum of all the capacities of the edges. So we can augment the flow network with a flow of 4 down the edges in our path and remake the residual network to show the changes. Only one edge has been pushed to capacity with this path. The residual network has edges in both directions for the other edges because they still have remaining capacity. We can now choose another augmenting path shown on the left. Note that this augmenting path is travelling down an edge representing the current flow. Up till now we've been adding the residual capacity to the flow network, but the edge chosen in the residual network opposes the flow in the flow network. This means we subtract the residual capacity from that edge. We've still added the residual capacity to the other edges because they go in the same direction in the residual network as they do in the flow network. However, we can see there is now no flow between node 6 and node 7. This may seem a bit counterintuitive, but we have increased the flow still. There is now a flow coming away from the source leading up to 8, and the flow which previously went from 6 to 7 has been redirected to go from 6 to the sink. This is not simply a case of just redirecting the flow, as we now have more water, or material, coming from the source into the rest of the system and more water flowing into the sink. Having sorted that out, we can choose another augmenting path. The residual capacity of this path is 14, and all arrows in the residual network path match the direction of the flow network, so we simply add the residual capacity to the flow. The edge from 3 to 4 is now at capacity, although other edges still have remaining capacity. This should be enough examples for you to understand the process, so to speed things up, I've chosen the path and performed the augmentation in the single step. Note that this path also redirects flow, in this case between 2 and 3. This is another path and augmentation, again redirecting flow, which previously went from 2 to 3. This path had a residual capacity of 5. To make things clearer, I have temporarily kept the edge from the source to 3, despite it having 0 capacity. This path also had a residual capacity of 5, as did this one. Using the edge from source to 1 with a capacity of 2, we can find and augment another path. This leaves only one edge remaining leading away from the source. There's nowhere for this path to continue to, however, so there are no more augmenting paths, and the algorithm stops at this point. Having terminated, we can calculate the maximum flow. We obtain the value of the flow by summing the flow out of the source minus the flow into the source. Note this is not the only possible distribution of flow along the flow network. Because we are choosing paths randomly, we may end up with a different flow network, but the same maximum flow if we ran the algorithm again. In this case, the maximum flow is 57. The runtime of the algorithm is quite simple to calculate. Each iteration of the algorithm increases the maximum flow by at least 1, and each augmenting path can be found in at least the order of the number of edges time. So there are at most order of the edges times the maximum flow iterations. Note that this algorithm is not guaranteed to terminate. It is only guaranteed that should it terminate, it will have found the maximum flow. Here's some quick definitions which we've covered. Feel free to pause. Note that it's the same as before, so we've just added the augmenting path and residual capacity. Here is the final overview of the Ford-Fulkerson algorithm. Thank you for watching, and I hope you understood that.